Welcome to the 30th session on measure theory. This is the third session on L1 spaces. In the last session, near the end, we proved some existence of denses or spaces of L1. We continue with that, and depending upon the time availability, I will also indicate applications. Usually, it's a done some kind of thing, dense subspace in LP space is generally done, but students are never given how to apply them. Okay. Some examples of applications. Okay. And also, many times the kind of things, many of the things, the details are swept under the rug. So, if you like analysis or you want to learn analysis and develop your critical thinking, I would suggest go through this video very carefully. Okay, I am sure that you will begin to like mathematics. What are the subtle points you must look at? And in all probability, what I am going to do may not be useful for passing exams or grades. Okay, if you are watching, I expect that you want to learn and they have good confidence in the subject. Okay, with this preliminaries which are somewhat warning in. Okay, let us get started. So what we want to prove, so let us start with this. B mu, okay, then we are defined L1 of x, B mu. We proved the simple functions are dense. Simple function in L1. Not all simple functions need to be here, but only those simple functions, let us call them as S. Okay, in L. This is a dense subspace of L1. Right? But if I specialize my x equal to R and B equal to the Lebesgue measurable sets and mu equal to the Lebesgue measure, okay, we have an interesting class of simple function, namely the step functions. So let us call this as ST, step functions. Functions in L1. Question is ST dense in L1? Okay, the answer is yes. Okay, as you by now, if you have intuition, you should see from step functions, what are they built out? They are built out of measurable sets, right? Since those are going to be in L1, that means each of the measurable sets, okay, which appear in the step functions. So let us, suppose f is in simple function, okay, and it's not all simple functions. Please notice that this notation only stands for simple functions in L1, right? If you write a canonical representation, the standard representation indicator of IEI equal to 1 to n, let us say, and we can as well assume CI's are not 0 for all I. Okay, and if f is in L1, then we know the integral of f is going to be summation Ci mu, in this case mu of ei, but it's just okay, right? If this is finite, if you want modulus, if this is finite, that means since Ci's are not 0, mu of ei's must be finite. Okay, each of them is finite measure, right? Once it's finite measure, in the case of R, when x equal to R, we know how did we compute the measure m of e? Start with any e, with the measure of e is finite. Okay, e is of course in a big measurable set. Okay, then we know that we can compute this. We found this measure by using union of jk k equal to 1 to infinity or jk's are open intervals, right? So, but your intuition should say roughly I want to do something here, okay, some kind of regularity. But let's try to motivate how I want to do that. So let me do a general setup. This will also help you when you go to functional analysis. Okay, suppose X is a non-linear space. That is, X is a vector space over RRC and with a norm. Okay, And suppose I have V, a dense subspace. Okay, right? And let's assume S is a subset of V is a spanning set. Right? Now suppose I have W, which is a subspace of V. Okay, I want to say W is dense in X. Okay, we want to claim, right? So what does that mean? For each A given any epsilon, give me any X and give me any epsilon. Okay, there exists an element W in W, so that norm of X minus W is less than epsilon. This is what I want to prove, right? What I want to claim is this W, okay, is going to be a finite linear combination. Let us say Ci of Si, I equal to 1 to n, where Si are and C, right? So if I can find for each S in S, okay, suppose there exists a W in W, so that norm of S minus W is, let us say, epsilon by n or epsilon by m, where m is max of mod Ci. At present, no, just to look at it, less than epsilon. Okay, so what does it mean? It says that any element of S can be approximated by W. That means for every W and for every S in S, and for every epsilon positive, there is the W in W, such that norm of S minus W is less than epsilon. Okay, then I claim if W, okay, suppose I have V in V, then V is going to summation Ci Si, right? So let me assume Ci's are not 0. If it is 0, it does not make any assumption, right? So let me assume Ci is not equal to 0 for all I, right? Then let m equal to C of C, m equal to maximum of, let me write C, it will be easier, maximum mod Ci. This is a finite thing, therefore it exists, right? Therefore, for each Si given epsilon, okay, given this, okay, for each I, let me produce a Wi in W, so that Si minus Wi, okay, is less than or equal to epsilon by n times C. This is true for all I less than or equal to n. This I can do that, right? Therefore, if I take my W equal to W1 plus Wn, this is in W because W is a vector subspace again. So notice that this is a vector subspace. Right? Now let us look at W minus B. W minus B is, okay, or B minus W. Okay, this is going to be C1 S1 plus Cn Sn minus W1 plus Wn. So I can rearrange the term. I go, all of you know what I want to do. It's summation CISI minus WI equal to 1 to n, and this is less than equal to summation norm of CISI WI. Okay, but what do I know? This is CI, I can take it out, therefore it's going to be 1 by CI. Okay, so each CI. So notice that this, what does this mean? This means C times SI mod CI times this. Okay, to put CI, I can take it out, right? Okay, so this will be less than equal to, each of the terms will be less than equal to epsilon by n times C, because mod Ci is less than equal to C. Okay, there are n terms, therefore it's equal to, okay, all right. So what I have shown, so in summary, let us do that. what I have shown is, if I want to show, suppose this is dense, these are all subspaces, okay, of X, and this V is spanned by S, okay. Then if I want to show W is dense in X, enough to show, okay, W approximates each element of S. Okay, what does it mean, approximate? We already know, given any epsilon, given any element S, and given any epsilon, there exists a W in W such that norm of S minus W is less than epsilon. This is what it means. This is essentially density. Okay, is that clear? So, pause, review, proceed. Now, how to use this? Let us look at, I have L1 of R, M mu, this is my space X. So, I have, yes, this is a dense subspace. This is a set of simple functions in L1. Right? Now, let's look at ST, this set of step functions. Remember, what is a step function? When I say f is a step function, what does it mean? F is going to be, see, a simple function such that this each ei is actually a ji. It's an interval. Okay, here I will assume it's an open interval. Okay. So set of functions. This is contained. This is a vector subspace of S. Okay, I want to say ST is dense in L1. So by the abstraction, what we know is, you give me any simple function f, okay, I want, and give me an epsilon positive, I have to show there exists okay. But notice that, let's go slow. So therefore, in S plus, yes, I have a spanning set. What is the spanning set for S? That is characteristic function of E, where A is in M and measure of E is finite. Notice, right? Do you remember? If F is simple and if F belongs to L1, then the standard representation, if I write it as summation Ci indicator function of Ei, then for Ci not equal to 0, the measure of Ei must be finite. Okay? So this is the indicator. Therefore, for whatever I said, to show ST is dense in L1, it's enough to show okay, for each E in M with the measure of E finite, there exists a step function F, okay, and epsilon positive. There is the step function F, so that the L1 norm of S minus indicator function of E is less than epsilon. Okay, make sure you understand this. Pause, review, proceed. Right? Okay. Now I want a step function. Step functions are built in terms of open intervals or intervals. In our case, I am going to deal with open intervals. So what do you think I will be making use of? That's what I said. I am able to think of the way measure of E is constructed using countable union of intervals, open intervals. Okay. Next thing is regularity. Okay. Let us see what it means. Since measure of E is finite, okay, there is an open set. Given epsilon positive, okay, there is an open set G in R, so that E is contained in G and measure of G minus E is less than epsilon. Okay, this is the inner outer regularity, we have seen it. Alright, but since we are on R, any open set G is a countable union of intervals, and these are pairwise disjoint. Right? Therefore, measure of G is nothing other than each one of them is measurable by countable additivity. It is measure of JK. But that is equal to length of JK. That is the definition of infinity. Now, given epsilon positive, epsilon is given. Therefore, I know there is a natural number n, so that okay, n plus 1 to infinity of length of JK. This is less than epsilon. Why this is possible? Notice that measure of J must be finite, right? Because measure of G equal to measure of E plus measure of G minus E. Okay, this is assumed to be finite. This is less than epsilon, therefore that's finite. Therefore, this series is convergent. Therefore, the tail end of the series must be as small as IP. Do you understand this? Okay. Now we are ready for a step function. Let's look at U equal to Jk, k equal to 1 to n, and look at this again. Remember, it's a pairwise disjoint. Therefore, if I look at I of U, which is summation of I of Jk, k equal to 1 to n, the indicator function. Okay, this is a step function, right? Now, what I want to show is, and notice that these are all in L1 because of whatever we did. Because this will be less than equal to Ik, k equal to 1 to infinity, but this is equal to I of G, but this is in L1 because measure of G is finite. Okay, I will stop for a minute, few minutes, then I will come back. Yeah, sorry, there are some things which I need to attend to. Let me continue. So let us go back. Now let's try to understand what we want to do. So we want to do show I of E, indicator function of E, and the indicator function of, how I define that? Yeah, U, right. Indicator function of U. Okay, this is less than epsilon or some constant times epsilon. This is what I want to show. Right? Now let's try to understand what really happens. This is again indicator function. Okay, many times it's boiled down to something like set theory. So suppose this is my A and this is my B. I'm just drawing simple picture. Don't worry about this. Okay, this is B and this is my A. Okay, this is my A and this is my B. Right? Okay. Now I want to know what will be I of A minus I of B. Right? Let us look at it. Okay. When this I of A of X, that means X must be in A, therefore it will be 1. And if it is not in B, it will be 0. Right? So you understand this? The sets which are involved is A union B. You understand that? The rest of things, maybe my X may be this. For any X outside A union B, I don't know to worry about. But A union B I can write as A minus B union A intersection B and union B minus A. Okay, this is A minus B. Let me make sure this is A minus B. Okay, and this is B minus A, and this is A intersection B. Correct? Yeah. So these are the cases. Suppose x is here, then IA indicator function here at x will be 1, this will also be 1, this will be 0, right? Now suppose it is here, x is in a minus b, then what happens? This is going to be 1, right? It's not in b, therefore it's 0, therefore it's 1. And suppose next is in b minus a, then what happens? It is not in a, therefore it's 0, this will be 1, right? Therefore, what we have found is the following. Let me write it. Therefore, I of a minus I of b equal to 1 if x is in a minus b, and minus 1 if x is in b minus a. Is it other way around? I hope I am right. Okay. If x is in a, 1 and minus b is 0, right? This is it is in 1 with b but not in, right, correct, and 0 otherwise. X is not in this. Let's say x is in a intersection. Outside is 0 in a way. Complement, it's always 0. Is that clear? Now interchanging a and b, what I get is ib minus ia. This is will be the other way around. Minus 1, 1, 0. This is a minus b, b minus a, and a intersection b. Right? Therefore, what is modulus of I of a, I of b, indicator function of a minus b? This is 1 in a minus b union b minus a, right? This is the symmetric difference of this. Is this clear? Pause, review, proceed. Okay. Now let's go back to our thing. So I have E, which is contained in G, and G minus E is epsilon, right? My U is equal to union JK, K equal to 1 to n, which is contained in G, which is 1 to infinity, JK, right? Now I am looking at I of U, indicator function of U minus E. And I of U is by definition is indicator function of JK, because these are all pairwise disjoint. That we had already seen. If A union B is pairwise disjoint, I of A union B is nothing else than indicator function of A plus indicator function of B. Okay, this is already known. Therefore, this follows 1 to n. I of U. Okay. All right. Therefore, I want to know what will this be. Therefore, this modulus is nothing else than indicator function of indicator function of symmetric difference, U symmetric difference of E, as we have seen earlier, right? Therefore, the integral of this I is nothing other than integral of I of U, its symmetric difference C. Therefore, it's measure of U symmetric difference C. Okay. Pause. Review. Proceed. Now, what is this measure? So U symmetric difference E is U minus E plus union this joint union E minus U, right? But U minus this is contained in G minus E is contained in G, therefore this G minus E union, this is going to be E minus U. Oh, what can I say here? I can't write this as E minus G. Yeah, this is contained in G minus U. Notice that I am using the fact U is contained in E and G is also contained in E. E is also contained in G, right? I am using this, right? Therefore, measure of U symmetric difference E will be by countable subadditivity will be measure of G minus E plus measure of G minus U, right? But this is less than epsilon. This one is nothing other than, remember, measure of G is summation 1 to n of measure of Jk, because countable additivity we already used, n plus 1 to infinity of measure of Jk, right? Therefore, this is also less than epsilon. Length of Jk n plus 1 to infinity. This is less than epsilon, therefore less than 2 epsilon. So what have we shown? So what you have shown is, if E is measurable with a finite measure, okay, there exists a finite sequence of intervals, open intervals, so that, okay, integrated function of E minus integrated function of union Jk, k equal to 1 to n in modulus, this is less than epsilon. Okay, this is what I call U, that is IU is a step function, okay, and it approximates IE. So this completes the proof. Step functions in L1 is dense in L1. So pause, review, proceed. Good. Okay. Now, why I took so much pain? So in the case of R, we have a much better class of dense of space in L1. What is they? They are the step function in L1, right? Now, how to use it? What is the application? Okay. This is something which you want to learn. Whenever you prove density, it's not just for curiosity's sake. Okay, we use density to do something which we cannot do in the for the general point. If D is dense in X, I want to say something about f of X or something to do with X, I may not be able to do it. I do it on D. From that, I see what will happen to when I do something similar thing to X. It's all vague, but we'll see in a minute what we want. Okay, let us go. So I may not be able to give the second application, but let us see. So suppose I want to talk about Fourier transform. Suppose f is an L1 function, y is a real number. Okay, I define f hat of y to be integral of f of x e power minus I over x dmx over r. Okay, notice that fx into e power minus I over x in modulus is mod fx. Therefore, this integral exists. Okay, this is actually L1, it exists. Is that clear? Yeah, make sure you understand this. So this function, this is a function of, think of this as a function of x, this function is dominated by integral function, therefore this function is also integral. Obviously it is measurable. Okay, right. Now what I want to do is I want to show f hat of y as a function from R to R or R to C. This is continuous. On R. Okay. For this, I don't need actually what I did earlier, but it will be fun to do that. Okay, it will be fun to do that. So let us look at, suppose I have a y plus h minus f hat of y. I want to estimate this, but this is by definition over R f of x e power minus iox into e power minus I hx minus e power minus iox. Do you understand how I did? Okay, I used linearity of the integral. Okay, and I got it. So this is obvious, therefore obvious thing is there is a modulus. Okay, keep the modulus out. I will do it later. This e power minus iox is a constant. So there I can take it. Therefore it is e power minus ihx minus 1 into dmx modulus. But that will be less than equal to, as we know, mod fx into modulus of this will be 1. Therefore it's modulus of e power ihx minus 1 dmx. Right? Now think of this as a function which depends on h. So gh, okay, of x by definition is fx into e power minus ihx minus 1. Okay, as h tends to 0 is f of x, and gh of x is bounded by 2 times mod of x, because this will be less than or equal to 1 each, 2 times mod of x. You understand? Therefore GHX converges pointwise. If you want, you remember when we did about various things, I can use dominated convergence theorem for parameterized family also. If you want, look at a sequence x and going to 0. Then define gn of x to be f of x into e power I hn of x minus 1. That's okay. Whatever I am saying will be true. There is no difference between h and n for me, right? Okay. So by dominated convergence theorem, the integral converges to where? So this converges to 0. I'm sorry, right? Why this converges to 0? Again, you have to see. Let us be very careful. G h of x equal to f of x, and I'm sorry, what I did was minus h of x 1, right? And since f is in L1, f is finite almost everywhere. That we know, right? And therefore, for those values of x where fx is finite, this converges to 0, because this will be finite. E power ihx minus 1 continuity of this fellow will go to 0. You follow that? Yeah. Therefore, what I know is gh of x converges to 0 almost everywhere, right? Therefore, I can use by dzt integral of ghx goes to integral of 0, which is 0. Is that clear? Therefore, what I have shown? I have shown that integral of f of e power I yx minus dx, okay, if it is f hat of y, then limit h to goes to 0 of f hat of y plus h equal to f hat of y, right? That means f hat is continuous function. Therefore, continuous on all. Okay, pause, review, proceed. Right. The next thing I want to say is, okay, this is an exercise. Modify the proof to show that f hat is uniformly continuous on all. You will later see it follows from what we are going to do. Now comes the next thing. This is the famous result known as Riemann Lebesgue Lemma. Most of you have done Fourier series, and okay, usually in BSc final semester or somewhere, or PDE, you or even ODE, you would have done Fourier series, and you would have seen f hat of n goes to 0 as mod n goes to infinity, right? That is called Riemann Lebesgue Lemma. Here it is for continuous version of the same thing. So what is that I want to prove? That is f is in L1, implies, then look at this function f hat of y as mod y goes to infinity is 0, right? Okay. What does this definition mean? This means given epsilon, there is an r positive, so that whenever mod y is greater than r, modulus of f hat of y is less than epsilon, right? Since we already know it's a continuous function, therefore my f hat, if f is in L1, implies f hat is in C0R, that is continuous functions vanishing at infinity. Right? So we need to prove that. Okay? We need to prove this is. So what do I want? I want to say limit y goes to 0, f hat of y is 0. Right? So this is where the density kind of thing comes. I know the set of step functions is dense. Okay? St in L1 is dense in L1. And each, if f is an L step function, then f is going to be summation ck I of jk, k equal to some 1 to n, where jk's are interval, open intervals if you know. Right? So I will prove for each j finite interval, note is that these are all finite because the length of jk has to be finite. That means jk's are finite intervals. So let us take j to be an open interval or closed interval, finite interval, okay, a, b, or an r, of course a is less than b. Okay, let f equal to integrator function of j. So I will prove that f hat of y goes to 0 as y goes to infinity. Mod y goes to infinity. Okay, let us prove this. This is very easy. Why? Because if I look at f hat of y, this is over r, this is f of x, e power minus iox dmx. Right? Notice that these are all the Riemann integral function. This is nothing other than therefore integral f of x e power minus iox dx minus infinity plus infinity Riemann integral. But this also, because my fx is integrator function, this is going to be a to b e power minus iox dx. Right? Therefore, by fundamental theorem of calculus, is minus e power iox by iy between a and b. I hope I am doing it correctly. Right? That is you. Okay. This is x equal to a and x equal to b. Remember that. Okay. Therefore, it is going to be e power I minus ya minus e power minus I y, maybe this is b, and a by iy. Right. Therefore, modulus of f hat of y equal to modulus of this numerator by modulus of y. And the note is that numerator is bounded by 2, therefore mod y. That goes to 0 as mod y goes to infinity. So what have we proved? If f is integrator function of interval ab, then we proved f hat of y goes to 0 as mod y goes to infinity. So pause, review, proceed. But that's not what I want. What I want is if f is in L1, then I want to prove f hat of y goes to 0 as mod y goes to infinity. This is what I want to prove. Right? But this means what? For if I give an epsilon, there is an r positive, so that modulus of f hat of y is less than epsilon for all y, so that mod y greater than r, this must happen. Right? So we do this simple trick. I know there is a step function, yes. Okay, for the given epsilon, there is a step function. With what property? yeah, f minus s in L1 norm is less than some epsilon by 2, epsilon by 3, something. But let's keep it as epsilon. Okay, but this is by density. This is dense in L1, therefore this is possible. Right? The next thing you should notice is this function f going to f hat. Okay, where is it? It's L1 to continuous function vanishing at infinity. This one. Notice that we already know this in L1 of R. We had already proved it earlier. Any such function is Lebesgue integrable. Okay, this function is linear, right? F plus g hat is f hat plus g hat, etc. Right? Therefore, this is very easy. Please verify. Therefore, f hat minus s hat is what I want to do. Right? Are you following? We know that. Then I want to say f hat minus g hat will be less than some epsilon. Let us make sure that is there. This is because f hat of y minus s hat of y is CMD some ck indicator function jk of y. Don't get intimidated. Understand what is happening. Right? But that doesn't matter. But what is this fellow? This fellow is nothing other than f of x and s of x, the whole thing into e power minus iox dmx over r. Therefore, in modulus, this will be modulus. This will be modulus. This will be less than 1, but this is less than epsilon. This is the L1 norm of f minus s less than epsilon. Right? So, what have we shown? If f is in L1 and s is its a function, then f hat minus s hat in L1 norm is less than epsilon. Or right? Now we are ready for the kill. So what I want to show, I want to estimate f hat of y, right? I want to say it goes to 0 as mod y goes to infinity, right? Therefore, what I will do is I will try to estimate f hat of y minus s hat of y. That means you give me an epsilon, I can find an r positive such that mod y greater than r should imply f hat of y modulus should be less than epsilon. This is what I want to show. Okay, so let me see that. So f hat of y is less than or equal to f hat of y plus s hat of y, sorry, minus s hat of y plus s hat of y. Is it clear? So if my s was a step function chosen such that norm of f minus s is less than epsilon, then we have shown this will be less than epsilon, and okay, this is universally true. But this will be less than epsilon if mod y is greater than r. You understand that? There is no condition on just y here. Right? But here there is a condition on y. So we have shown that if mod y is greater than r, f hat of y is less than 2 epsilon. So we have proved that. Okay, the Riemann Lebesgue Lemma, which said that f is in L1 implies f hat of y limit mod y go to 0, sorry, infinity is 0. So go through the proof once again. See, I like this kind of application because you can see how much of measure theory, integration, etc., various facts we have to use, and it makes us appreciate what we learned earlier, and that because we have to use it, we are trying to understand what we proved earlier also better. Okay, so you should that is why one should also solve problems or always find applications of any result. That makes us confident. Okay, so this finishes one of the very important application, a non-trivial theorem. And if you want to appreciate how the density help, I think you should look at some of the classical book. If I remember right, when I was an MSc student, almost 50 years ago, okay, I learned Riemann Lebesgue Lemma the hard way. If, I think I learned it from Tishmar's theory of functions or some such place. Okay, you can see they start with F in L1 and they have to do a lot of work. Whereas we saw how it's very trivially proved, only I have to verify Riemann Lebesgue lemma for a indicator function of an interval, right? And after that, everything follows by very standard trivial analysis using density, etc. So appreciate that. This is a very important thing. Okay. So the second application is, do you remember we proved continuous function with compact support R in L1, and that set is, that space is dense in L1. You want to give an application of that. Again, you will learn a lot of analysis. You will understand. I really hope at least 10 to 15 viewers of this particular video will go through it carefully and appreciate. Okay. As I said, it may not be useful at all to get a good grade, but it will be useful if you want to face interview later or you want to do analysis, higher analysis. Okay, you will learn it. Okay, stay tuned. We will continue. I find that 46 minutes, almost 47 minutes are over. Okay, the next one will also take perhaps about half an hour or so. So it will not be good to do that completely. But I will do something which is common to the application 1 and application 2 next 10-15 minutes and stop there. Okay, and the second application will be next video. Okay, I really request, if you are interested in mathematics and especially want to be good in analysis, okay, and want to pursue functional analysis or harmonic analysis or PDE, please go through these things carefully. Okay, so this is some kind of a gap, a bridge between application 1 and application 2. Okay, what you have seen in application 1, it has something more, and what we are going to do, this part I need for application 2. That's why I just think of it as a gap bridge. Let's do it. Do you remember we define a function f from R to R, okay, is in C0R, that is continuous function vanishing at infinity. For example, if f is in L1 and the Fourier transform is a continuous function vanishing at infinity. We proved it, right? Okay. So what I want to prove is such functions are uniformly continuous. Okay. In particular, any function, yeah, which is continuous function with compact support, that will also be uniformly continuous. Okay. Because CCR is continuous Z0R. Because after a certain R, mod x, if mod x is greater than R, my f of x will be 0 if f belong to this. Alright? Therefore, it's actually a continuous function vanishing at infinity. Let us again recall the definition. For any epsilon greater than 0, there is R positive, so that mod x greater than R implies mod fx is less than epsilon. Right? This is what we proved for in Riemann Lebesgue Lemma. Okay? Is that clear? And this one is often used. Many teachers, students assume it's compact, continuous function compact, said therefore it has to be uniformly continuous. Okay, that's a correct intuition, but if many people will not know how to write a careful proof for that. Believe me. Okay, so the proof which I am going to do is exactly adapting the proof for this only. Okay, so you should be able to write down the proof. So let us go back. So I want to prove uniformly continuous. Let epsilon greater than b0. Therefore, what I know is since f belongs to C0, it's a continuous function vanishing at infinity. Okay, there exists R positive, so that mod x greater than R implies mod fx is less than epsilon. Right? So I have minus R to plus R. Then let's look at minus 2R to 2R. Right? Then what I want to say, f is uniformly continuous on not necessarily, of course on minus R to plus R, but I want to say 2R. Do you agree with that? Because now I can use this is a continuous function on a compact set. Therefore, it's uniformly continuous, right? Therefore, for the epsilon you gave me earlier, okay, there is a delta positive, so that if x and y belong to minus 2r to plus 2r and mod x minus y is less than delta, I know mod fx minus mod fy is less than epsilon. Right? Now what I want to say is the same delta works for R. It worked only on minus 2R to plus R, but on the entire real line it works is what I want to say. So let us start with x and y in R, so that mod x minus y is less than delta. Then I want to prove mod fx minus fy is less than epsilon. This is what I want to prove. Yeah? Right. So, as I said earlier, if x and y belong to minus 2r to r, no problem. Right? You understand? And suppose x and y lie outside this, okay? So it's okay. Now with the laws of generality, I can assume my this delta is such that delta less than r, right? So I have 0, I have r. If it works for some delta, I can go below this. For every delta less than that also it will work. Therefore, I can assume my delta is less than r, right? So if x and y both belong to outside, then also it's true. Because notice that either x and y have to be here. This is minus 2r, this is 2r, and it cannot be one here and one here, right? Because the distance will be greater than 4r. But the distance between x and y is less than delta, but delta is less than r. Therefore, either they have to be here or they have to be here. Is that clear? Yeah. But if this be the case, then mod fx minus fy is less than mod fx minus mod fy. That is less than 2 epsilon. Right? So I could have chosen epsilon by 2, make sure. Okay. So this case is okay, this case is okay. Then what is left out? The left out thing is 1. So x is mod x, let us say mod x is greater than 2r and y is not any element. And mod x minus y is less than delta. Then I want to know mod fx minus mod fy is less than epsilon. Right? Now you will see I will go back to this. So if x is greater than 2r, right? Now where is y? Let us look at this. See, look at mod x, 2r is greater less than mod x, but mod x is less than or equal to mod x minus y plus mod y. But that's less than or equal to delta plus, it's actually less than delta plus mod y. Therefore, mod y is greater than or equal to, or strictly greater than 2r minus delta, but that is 2r minus r greater than or equal to greater than anything. I don't care. This one. So both x and y, x is mod x is greater than r, that means mod y is also greater than r. Sorry, mod x y is greater than 2r, mod y is greater than r. Right? Therefore, what do I get? Therefore, f of x minus f of y again less than equal to mod fx plus mod fy. Right? Now mod x is greater than r, 2r, therefore this will be less than epsilon. Mod y is greater than r, therefore this will be less than epsilon. Remember, for the given epsilon, how we chose r? Okay, therefore it is less than 2 epsilon. So we have proved for all x and y in R, if mod x minus y is less than delta, mod fx minus mod fx minus fy is less than epsilon. Therefore, f is uniformly continuous. What is f? F is a continuous function vanishing at infinity. So go through the proof. With this we will stop. In the next one, again it will be a very good thing, because when you are going to do, for example, simplest case I can think of is next year semester you are going to do functional analysis sometime, right? There you will see this operator. Okay, many times that operator is not carefully established to make sense, that it makes sense. Okay, we will do all that thing. Our main painful part will be to show it makes sense, some operator. Okay, then we will show something about continuity. Okay, please stay tuned. We will meet again. Take care and stay safe.